Hello and welcome to Homework 1 Part 2. In this part of the homework we are taking a look at somewhat similar of a problem that we had in Part 1. However, there is a big difference in it. And this time we're going to have 3 consecutive tanks. And what is going on here is that we have some flow rate into our first tank. And then out of our first tank we have a hole in the bottom of it that is flowing into the second tank. And then a hole in the second tank and some flow rate going into a third tank, and then ultimately some flow rate going out of the third tank into wherever else. So what we have here again is some flow rate in and some height of the first tank, some flow rate going from tank 1 to 2, so we'll call it Q12. Then we'll have some height of the second tank and flow rate going from tank 2 to 3, so Q23. And then height of the third tank, and we'll call that Q3, leaving this setup. So what we're going to say here is that initially we are at a steady state. So all the heights of the tank, the fluid level and the fluid heights in the tanks are all equal, and the flow rates are all equal. And what we're going to do is, I believe we're going to do something similar in part 1, which we multiplied it by, or we changed the flow rate, or we increased it by 20%. So we'll be multiplying it by 1.2. And we want to derive expressions to see how these, the fluid heights in the tanks change over time. So what we can start here with is our change in volume with respect to time. So if we look at tank 1, we know that this change in volume with respect to time will be equal to Q in minus Q12, because Q12 is the flow rate leaving tank 1. Now what we can do is break this down even further to get into dH dt for tank 1, so the change in height, fluid height in tank 1 with respect to time. This will be equal to Q in minus Q12 over AC. So essentially here what we're going to have is 3 different differential equations. We use the same solver, solve IVP, except this time we'll have a vector of 3 differential equations. So this is what we'll plug in, and we'll have 3 expressions. So dH 2, so the change in height, the fluid height of tank 2 with respect to time will be equal to Q12 minus Q23 over the cross-sectional area. And same holds true for tank 3. Now what we can also say here is that Q12 is equal to 2 times G times H1, and this will be raised to the 1/2 power. And I believe, yeah, we have to end up multiplying this by the area of the hole. And what we're also going to say, I forgot to say this, is that the area of the holes for the flow rates leaving each tank, we're also going to say that they're the same for each. So we have fluid height levels the same, and cross-sectional area of the hole at the bottom of each tank are the same. So what we can do is head on into Python and plug this into our solve IVP, and then plot it to see how the fluid height levels change over time if we raise our flow rate into the first tank by 20%. Okay, so I've gone ahead and imported in some numerical tools that will help us solve these differential equations. So NumPy, poly dot subplots so that we can graph, and SciPy integrate so that we can solve the differential equation. So what we're going to say here is that the size of the hole at the bottom of each tank is all the same, and it is 0.01. The cross-sectional area of each tank is 1. We have the gravitational constant here, and we have the initial flow rate into the first tank being 0.1 cubic meters per second. We still have our H naught expression that we used in part 1 of this homework, and we have some timestamp here which we can change around once we get to plotting. But what we'll go ahead and do here is define a function here. So we'll define the right hand side, which we will eventually throw into solve IVP so that we can solve it. We have our independent variable time here and a vector of our dependent variables. I'll just call that v. And what I'm going to do here first is just unpack that vector of dependent variables. So I have h1, h2, and h3 are equal to v. And I'll go ahead and set in qn to be equal to 1.2 times qn naught, because we will be raising that initial steady state flow rate by 20%. Then we can calculate our Q12, Q23, and then Q3, which we know is AH times 2 times G, and then times H1 for the first tank. And this will be raised to the 1/2 power. So I'm going to go ahead and copy this for Q12 and Q3 here. So Q23, we'll be using the height of the second tank, and then Q3 is dependent on the height of the third tank. Okay, so now what we can do is go ahead and return, and we're going to return all three of these. So we'll have NP, an NP array here, and the first one we'll have is Qn minus Q12, so Qn minus Q12 divided by AC. Put these in parentheses here. Then we'll have Q12 minus Q23 divided by AC. And then lastly we have Q23 minus Q3 divided by AC. I think we have everything matched up there. Let's go make sure it runs here. Okay, so now we can go ahead and plug into solvi BP. So go ahead and basically unpack the solvi BP here, and let's run it. So solve IVP. I have the right hand side, our timestamp, which is 0 to t end, and then we will have our array of initial parameters here. And since they're all the heights are the same, it'll just be h naught, h naught, and h naught. So h naught, h naught, h naught. We're going to use a method of computation here of L soda. Oops. And dense output we'll set as true. Okay, let's make sure that we made no errors here. Let's see here. Invalid syntax. Need a comma here. Okay. Okay, so now we'll go ahead and plot this out. So we'll create a tplot variable and create some linearly spaced out points. So we'll go np linspace. Oops. np linspace from 0 to tn, and we'll do 100 of them. And then we'll unpack that that result that we get from our solve IVP into H1, H2, and H3. So H1, H2, and H3 equal res solution tplot. And we'll go ahead and plot this up. So fig equals make subplots. Then fig dot add scatter. We'll do it for the height of tank 1, the height of tank 2, and then the height of tank 3. So we'll have our tplot linearly spaced points for our x, and for our y we will plot h1 here. And I'll go ahead and name it tank 1. Okay. And then I'm just going to Control C for the height of tank 2 and then the height of tank 3. So have H2 here and tank 2. Then we'll have H3 and tank 3. And I'll go ahead and see if this makes sense here when we plot it up. So it does. It definitely makes sense if we look at the graph here. If we look at tank 1, tank 1 starts to rise as the fluid level jumps up that 20% increase. And then because of that rise in the fluid level of tank 1, that causes the fluid level in tank 2 to rise, which therefore dictates the rise in tank 3's fluid level. So after plotting it out, we do know and we can see here that it does make sense. So that's how we can verify that what we have derived is indeed correct. So that will be it for part 2 of this homework. Thank you.